This is section 13.4 on cross products. The main goal here is to figure out what is the other kind of product, since we did dot products in the previous section. So the objectives are we need to be able to find the cross product. We want to be able to understand and verify some properties of the cross product, both algebraic and geometric properties. And then we'll see a couple of applications of the cross product, torque and the volume of boxes and, well, the parallelogram equivalent of boxes. So let's jump right in. What is the cross product? Instead of writing u dot v, which is our notation for the dot product, we write u cross v for the cross product. The cross product of two vectors is a vector. So this is the main thing that is different from the dot product. Like when you take the dot product of two vectors, you get a scalar. When you take the cross product of two vectors, you get a vector. So this is also sometimes referred to as the vector product. Anyway, what vector do we get when we cross two vectors? Well, we get a new vector, u cross v, and the magnitude of u cross v is the magnitude of u times the magnitude of v times the sine of the angle between them. So this is our definition. When you cross two vectors, you find the angle between them, you make a new vector that has this magnitude, the product of the magnitudes times the sine of the angle. Now, that's not enough information to tell you what the final answer is, what u cross v is. We also have to tell you a direction. And the direction is given by this thing called the right-hand rule. So what you do is you take u and v. You point the fingers of your hand of your right hand, it has to be your right hand. You point the fingers of your right hand down u, and you curl the fingers of your right hand toward v. If you do that, if you can do that, then you have your hand in the right direction, and your thumb points in the direction of u cross v. And this seems completely absurd, but this is actually how we decide which direction u cross v is pointing. If you did v cross u instead, you would end up trying to curl your fingers the wrong way, and so you would realize, oh crap, if it's being crossed in the other direction, I have to turn my hand over to curl my fingers this way, and then that tells you that the cross product points the other direction. This decision was kind of like an arbitrary decision. We could have defined u cross v to point the other way if we wanted to, just like we could have defined electrons to have positive charge, but instead at some point we just picked that electrons have negative charge. Now that we've picked this direction, we're stuck with it, and we can write down all the properties of it. Okay, so how do we actually calculate the cross product? To calculate the cross product, we'll find that what we'll do is we'll take u, which is u1, u2, u3, and v, which is v1, v2, v3, and put the components of each vector in a matrix like this, a 3x3 matrix, where the top row is ijk. Then you take this whole thing and you take the determinant of the matrix. Okay, how do you take the determinant of a matrix? The determinant of a 3x3 matrix is you can go across the top row. You pick I first, cross out the i's row and column, and do I times the determinant of this smaller matrix. Then grab the second component of the first row, cross off its row and column, and see what's left, and do the determinant of that matrix with a minus. And then do the same thing with the last one, cross off its column and row, and there's a smaller matrix sitting there. What are these? Well, these determinants of smaller matrices you get by going, you take the two diagonals and subtract them. So for the first one, I would end up with, this is what's in the I component, u2 v3 minus u3 v2. And then in the j component, I have this minus here, u1 v3, that's this diagonal, minus u3 v1. And in the k component, I have u1 v2 minus u2 v1. This is how determinants work. If you've never seen determinants in any math class before, this is a big topic that comes up over and over in like linear algebra, which linear algebra is going to sneak into your math career more and more as you take more and more math classes. Determinants are used in tons of different things. This is just one application of a determinant. I'll show you another shortcut for how to find these in a minute, but this is how you find a determinant, and it's called expanding on the first row. Okay, let's find some cross products. So I'll do one of them using this method and the other one using a different shortcut, and you can pick whichever method you like better. So the method that's given here in this cloud is that you should put I, J, K along the top row, and then 3 minus 2, 4, that's U in the second row, and put V in the third row. And then expand along the first row. So we'll have I times the determinant of whatever's left when you cross off I's row and column. Then minus J times something, and plus K times some other thing. So for J, I cross off J's column and row, and I have a 2 by 2 matrix left over. It's 3, 4, 5, 2. And for K, do the same deal. Cross off K's column and row. And I get this. Each of these determinants is a number, and the end result will be a number times I, a number times J, and a number times K. So I'll get a vector at the end. So here's what's in the I slot. Minus 2 times 2, minus 4 times 1. For J, I've got 3 times 2 minus 4 times 5. And for K, I've got 3 minus 10. This was K. So the final vector is I've got minus 8 in the I slot, minus 14 in the J slot, and 13 in the K slot. So I take two vectors, I take their cross product, and I end up with a new vector. And it's a new vector that's pointing in the direction where, like, if that way was U and this way was V, then the cross product would be pointing in the direction of my right thumb there. Okay, we'll also find V cross U. When I do V cross U, I'll just do it the other way that I know. There's tons of ways to find determinants, but for 3 by 3 determinants, this shortcut works, and so I'll show it to you. If you want to find the determinant of a 3 by 3 matrix, you can just copy the first two columns again. So you write down the whole matrix, and then you copy down the I and J column a second time. And then what do you do with this? Well, you find all of the diagonals, and the diagonals that go forward, those count positive, and the diagonals that go backward, those count negative. So let me show you what I mean. Here's one diagonal, it's minus 4i. I multiplied I times minus 2 times 2. And then I multiplied J times 4 times 5. And then I multiply K times 3 times 1. And those all count positive. And what you'll notice is that these are just terms that appeared earlier in our other way of calculating. This just finds them a different way. Then the backwards diagonals that find 3 terms, those all count minus. So I have minus 10k, 4i, and 6j. And if I add those together, I get minus 8i, 14j, and minus 13k. So you get the same stuff, like it's the same amount of arithmetic work, but it's a different kind of organization, and you can do either method if you're dealing with a 3x3 matrix, which is what we're dealing with here. This method of expanding and making it into smaller determinants works for any size matrix, so if you end up in a linear algebra class, you'll absolutely need to know this top way. If the only application of determinants you've ever seen is the cross product, then this is a totally fine shortcut to find the determinant of 3x3 matrices, because we'll only do this for 3x3 matrices. Okay, what are you supposed to notice here? Well, what you're supposed to notice is that we found u cross v and we found v cross u, and they were about the same, except no, not quite. Uh-oh. We were supposed to get... Oh no. I actually didn't find v cross u. I found u cross v again. Because I just put u in the second row and v in the third row. Okay. So this was just two ways of getting u cross v, and you get the same answer both ways. If you instead find v cross u, what happens is you put v in the second row and u in the third row. And if you do that, you get the opposite answer. So I guess I'll leave this as u cross v. If we do it in the opposite order, the point of this was that you were supposed to see this, you get the opposite of u cross v. The reasoning for this geometrically was that with the right-hand rule, if you have two vectors and you do this one cross this one, then you would go, your hand would curl this way and the cross product would point up. If you instead tried to do it in the other way, you'd have to flip your right hand over to start at v and do v cross u, and then your thumb would point down. So you'll get the opposite. Oh well. Okay, let's write down a couple of properties of the cross product, how the cross product works. One thing to notice is that the cross product only works in space. So only in 3 dimensions. If you're working in 2 dimensions or 4 dimensions, you don't get to use the cross product. It doesn't work at all. The dot product works in all dimensions, but the cross product is like stuck in 3 dimensions. It actually turns out that there's a corresponding kind of product that works in 7 dimensions, but we won't get to that in this class. Anyway, here's some properties of the cross product. The first one is this one that I've said a couple times, is that if you do the cross product in the other order, it's not commutative. You actually get the opposite result. What else do we get to do? We get a distributive property. If you cross with a sum, then you can distribute the cross product. There's a scalar multiple, and the scalar multiple works the same way that the dot product scalar multiple worked, which was if you have a scalar and you cross it with a if you have a scalar and you multiply it by a cross product, you don't distribute the scalar the same way that you don't distribute 2 times 3 times 4. Like, you don't distribute the 2 here. You either multiply the 2 times 3 or you multiply the 2 times 4. You don't like use it twice. And similarly here, you can either put the c on the u or you can put the c on the v. So the cross product works like multiplication in that way. There's a couple of easier issues here, like if you go ahead and cross with the 0 vector, then all of those products will all be 0, and so you just get the 0 vector back. It doesn't matter what order you do if 0 is involved in your cross product, you're getting 0 as the answer. One other thing is that if you multiply a vector by itself using the cross product, you get 0. This is a little bit surprising maybe. If you dot a vector with itself, you get something else. You get its magnitude squared. So dotting a vector with itself is often useful. Crossing a vector with itself, not so much useful. Finally, there's a really nice property, which is, is it called trilinearity? Oh crap, I can't remember now what it's called. Well, this is called the triple product. If you have three vectors and you dot one of them with the cross product of the others, it will turn out that you can instead cross the first two and dot with the third one. And this is like really weird. The others make perfect sense. Like this, based on the first one, based on the right hand rule, like that's how it has to work. These, I don't want to call it a product unless these behave the way that they behave. The cross of something with itself equals 0. That's kind of maybe surprising, but what we need is we need a vector whose magnitude is the magnitude of the first one times the magnitude of the second one times sine of theta. And the angle between a vector and itself is 0. Sine of 0 is 0, so you get 0. So whatever this vector is, it has a magnitude of 0, and that's the 0 vector. This one's just weird, but it's okay. Yeah, we don't have a class period. It's unfortunate. So I can't have you like talk to each other and try to justify these things. Okay, what is the cross product actually used for? Up there is just like what we kind of like when we're calculating with the cross product, what properties will be useful. This is like, what's the point of the cross product? The point of the cross product is that if you cross two vectors that are parallel, using the same argument I just used about sine of 0 degrees, you get the 0 vector. But it's even stronger than that. If you ever get the 0 vector by crossing two things, that means that you must have had two parallel vectors. So you can, just like you can use the dot product to detect whether two vectors are orthogonal, you can use the cross product to detect whether two vectors are parallel. And then what's the geometry purpose of U cross V? Well, if U and V are the sides of a parallelogram, so what? How do you make a parallelogram out of two vectors? Well, you like copy V down again over here, and you copy U down over here. You get a parallelogram, and the area of that region, of that parallelogram, is the same as the magnitude of U cross V. So this is a geometric description of what in the world the cross product is doing. Like the first geometric description was that we can figure out which direction the cross product is pointing using our right hand. But okay, how far should we go in that direction when we find the direction? Well, you look at U and V and you find the area of the parallelogram. When you do that, that's the magnitude of the vector. And the reason for that is like pretty simple. I guess I'll do it on the next page because I don't want to try to write everything down here. Okay, so let's prove the two things. This one was that U cross V is 0 if and only if, so both directions, if and only if U is parallel to V. Okay, to prove this, we go both directions. We first assume the left side and show that the right side is true. Then we assume the right side and show that the left side is true. And then from then on, the two facts are interchangeable. They're equivalent. So let's suppose we have two vectors where their cross product is 0. I'm trying to show that U is parallel to V. Okay, if U cross V is the 0 vector, then we know that the magnitude of U cross V came out to 0 because the U cross V is 0, so its magnitude is also 0. Well, how can that happen? we know that the magnitude of u cross v is magnitude of u, magnitude of v, sine theta, which means that one of these three components must equal 0. This one says that they're parallel. This one says that one of the vectors are 0. Did we have in our fact that like the vectors are non-zero? Okay, here. So if the vectors are non-zero, then we can't have any of these. So the vectors are parallel. If you go the other way, you suppose that the vectors are parallel. This is like kind of silly, but whatever. Let's suppose that the vectors are parallel, that one is a multiple of the other, that u is a multiple of v. Then what you can do is say, let's cross them. We're trying to show that their cross product comes out to 0 in this case, so you substitute cv in for u. Notice that you can factor a constant out of a cross product. And then v cross v is 0, so you get a multiple of 0, which is 0. So either way, if the cross product is 0, or if you know that the vectors are parallel, you get the other fact, so the two facts are equivalent. For the second one, let's just draw that picture that I had before. I have u, and I have v, and I have a parallelogram made out of them. And we're trying to find the area of this parallelogram. Well, the area of a parallelogram is its base times its height. I don't know why I made the base a capital letter. Let's fix it. The height is this height, where we drop a perpendicular. The trick here is, well, the base is just the magnitude of v. Well, what's the height? The height is a component of u. If we drew this angle here, then this distance would be the magnitude of u cosine theta. And this height is the magnitude of u sine theta. So when you're finding the area, the base is the magnitude of v. The height is the magnitude of u sine theta. And that's it. Because this here was our definition of what the magnitude of the cross product is supposed to be. So the area of a parallelogram, because of how we defined it, that like its magnitude, because of how we defined the cross product, that its magnitude is given by this formula, the parallelogram has the same area. Okay, these sections are always a little tricky because like you listen to the whole thing and then you go do problems, but let's try to recap what we've done so far. So you've got the definition of the cross product, which says it's a vector with this length that goes in a direction that has something to do with the right-hand rule. Then you say, okay, that's nice. The right-hand rule tells me geometrically what the cross product means, but then the parallelogram picture, tells you geometrically what this formula means. So you have kind of like algebra and geometry ways of thinking about the cross product. When it comes to actually calculating the cross product, you're probably not going to draw the two vectors, draw a parallelogram, and find the area. Instead, you need some like algebra method to find them, and that's what that determinant stuff was for. So hopefully you get to practice all those in the homework. Okay, let's do a couple of questions. If u and v are orthogonal, what's the length of u cross v? Well, if u and v are orthogonal, then the angle is 90 degrees, which is pi over 2. So the length of u cross v, well, I have a formula for the length of u cross v. It's the length of u, length of v, sine theta. And theta is pi over 2, so sine theta is 1. So if u is orthogonal to v, then the length of u cross v is just the product of the two vectors, of the two lengths. It's kind of cool. I do not know what's going on with this. This looks like some kind of typo. This looks like it's supposed to be u cross v plus v cross u. If you take u cross v plus v cross u, well, v cross u is the opposite of u cross v. So you end up with u cross v minus u cross v, and you get 0. One small thing here, this 0 is a little bit confusing, but cross products are vectors, so the end result should be a vector. Okay, this third one is really cool. What does coplanar mean? Coplanar would mean that all three of the vectors sit in the same plane. So, like, given two vectors define a plane that goes through the vectors. Like, if you have two vectors, you can have a piece of paper and just put the two vectors on that piece of paper, and that's the plane of those two vectors. If the third vector, w, also is in that plane, then you say all three are coplanar. Well, why would that happen? Here's the trick. V cross w is orthogonal to both v and w. So you take v and w, if you find v cross w, you would like put your right hand pointing at v, and you'd curve it toward w, and then your thumb points which way, the thumb of your right hand points which way it goes. So this needs to point like back into the paper. This is v cross w. If u dot v cross w equals 0, that means that u is perpendicular, it's orthogonal, to v cross w. This is the point of section 13.3, is that if a dot product is 0, the two things that you dotted were orthogonal to each other. So v cross w is the normal vector to v and w's plane, but u is orthogonal to that orthogonal thing, so u is trapped in this plane with v and w. Yep. Okay, on to the last page. The last application we'll do of cross products is that they're good for torque. So the torque is the tendency to rotate. Yeah, if you take a paper cutter and there's like a hinge here so that the paper cutter can go up and down. Well, if you say like took your hand and like pressed down on the paper cutter and pressed it straight down right here, you would get the paper cutter to swivel. But it would be more efficient to take your hand and push this way, like pull this way. Can you imagine that? I don't know if you know that. Like that pushing down is not as efficient as like pulling the lever the way that the lever is going. Other things that you may know from trying to like turn objects is that it's easier to turn it when it's out here than if you like put your hand up like down here toward the hinge and push down. You would have to use more force to turn it. This is the concept of torque. So what affects your ability to rotate this lever or this arm? One is how far away you are from the hinge. So this is the length of the arm. Another is like how hard you try, so the force applied. And the last thing is the angle that you choose, like choosing this way versus this way. Well, it will turn out that the torque, when you put all of those, all those factors together, you end up making a formula that looks exactly like our cross product formula. The torque is given by, well, call this R, and say the force that you put on it is a force F, which will also be a vector because it has a direction and a length. just like this arm, it has a direction and a length. So say you like pull down this way. The length of the arm is one of the factors. The amount of force is another factor. And then perpendicular makes your force more effective. So like if you just pushed in on the if you just pushed inward on the arm, you wouldn't get any force. So we want sine of theta. Theta is our angle between the two vectors. This is the same thing that we had in our definition of the cross product. So this is another way to visualize what the cross product actually does, is that the magnitude of the cross product of these vectors is the amount of the torque. This T is not this. It's the magnitude of T is this. So I guess we're going to go like this. If you get into a better, more advanced physics class, you'll define what T actually is. And I just don't really want to talk about it. But the magnitude of the torque, like how much effect you get from this, is you take the cross product of the two vectors and take the magnitude. You can guess what you should do to get T, like based on this equation. But we're just going to go with the magnitude because this isn't a physics class. So how do you do this? Well, you say, okay, I've got a lever arm of length 3 feet. I'm doing 10 pounds of force at this angle, and I'm trying to like spin this lever. Well, the amount of torque is the length of the arm times the amount of the force times the sine of the angle. Yeah, that's it. We're going to get foot-pounds, which is the proper unit for torque in like imperial measurements or whatever. Sine of 30 degrees is a half. So I get 3 times 10 times a half foot-pounds, which is 15 foot-pounds. If you just make the arm shorter and you leave everything else the same, you just make the arm half as large, then you cut the torque in half. And this would be the same as if you took this force and pulled on the middle of the lever. That's not useful. So here you get half as much torque. So you get 7.5 foot-pounds. If you instead go to the end and you actually pull at a right angle, now you're going to get the amount of torque is 3 feet times 10 pounds times the sine of pi over 2. But the sine of pi over 2 is 1, so you get 30 foot-pounds. So the easiest, the most effect you can get out of your turning action is to go all the way to the end of whatever arm you're looking at and pull perpendicular to the arm. Yeah, here, just changing the angle doubled our amount of torque. Going closer to the rotation, closer to the hinge here, cut our torque in half. Yeah, so you want to be all the way at the end as far as you can and pull perpendicular to the arm. That's it. Okay, so go do some practice problems. Mainly, like, I didn't focus very much on how to find the cross product using these determinants, so you need to practice some of that because you'll be finding cross products throughout the class. Yeah, and then you'll end up using some of the properties.